can take a look at the syllabus, all the details that are involved in that. If you don't know what a syllabus, you'll understand when we finish that. We're also going to go into your first notes, and we're going to do your first lab. So I promise we will be out of here no later than, let's say, 8:30, 9 o'clock or so. Okay? And of course, you know I'm teasing, right?
Yeah.
Okay? Class ends 7:15. Okay? If we get out earlier, that's fine. But yes, we are going to do a lab. I do have a very strange sense of humor. What I'm going to start with is a little bit about what my background is. When I was in 8th grade, my earth science teacher made us go out and collect rocks. And I thought that was the stupidest thing possible. You know what it's like when you're in 8th grade. And what I did not know at that time, that I was living on top of an ancient lava flow in New Jersey. If you can see these red wiggles, these are called the Watchung Mountains, right here, all of those. All right, those over there as well. The Watchung Mountains formed many, many years ago, when, and that's where they're approximately located, when New Jersey and Africa slammed together. And when they slammed together like this, they eventually pulled apart. The Atlantic Ocean did not exist at that point. And when they pulled apart, New Jersey cracked open in a number of very, very long cracks, something similar to this. And then lava spilled out, kind of like what you see over here. And of course, this is not from that time. Here is where the long split would be. This is referred to as a rift. And when the lava spilled out, it made these gigantic lava lakes, as you can see over here. And then those lava lakes solidified. And then as New Jersey and Africa continued to pull away from each other, what happened was that these lava lakes tilted. And then most of those lakes, now San Juan, was buried underneath the ground. And here you can see the three Watchung lava flows. These are all underground. Right here, these are all buried. And the part that's stuck up here, here, and here, plus in other places as well, is what we would call the Watchung Mountains. So you would see the edge, and that's where you see the housing development all the way to the very top. This is the edge of the ancient lava, at least one of the ancient lava plates. So our teacher made us go out and collect all of these rocks. And no, this is not me, but I had to go out and collect these rocks, and then eventually learn to identify the rocks and the minerals. Now, what happened with the lava flows is that there were some holes in the lava flows as the lava solidified. Some of the holes were this large, others were a lot smaller, like you see over here, and crystals started to form inside of those. And it would be really nice if I had found something like that, because the color's off a little bit. But those are some beautiful crystals in what's called a geode. And I didn't find stuff as nice as that. I found stuff similar to this. I did not find this, but similar to this. And I started to find out, to learn how to identify what these minerals were. And that really got me interested in the earth sciences. Also at that time, or actually a little bit later on, I should say, there was a special mine that eventually was opened up into an educational center. And this is in Ogdensburg and Franklin area in Sussex County. And you can go into the mine today. All right, so now it's a big educational thing. They bring groups of people in. If you lived here in New Jersey, you possibly learned that when you were in younger grade. They allow you to pick up these fluorescent minerals, things that you would say glow in the dark. And that really got me interested in this. So I went to school to major in earth science. I went here to Keene, but that's when it was called Keene College, a long time ago, not in 1855. And then after I got my bachelor's degree here, I decided I would work on a master's. I worked on two masters at the same time, one here at Keene, one at Rutgers, something I would not suggest doing, so a little bit on the hectic side. Then I tried for a doctoral degree at Rutgers, didn't make it, but I got out of there with a specialist degree. And what that really taught me is that all of my classes cannot be the way my classes were given. We would show up in a classroom, the professor would put stuff on a screen, that's when we used overhead projectors, and they had typing on there, something you can't even read. And they would talk for 3 hours, and that was a science class. Doesn't work that way. I run all of my classes as hands-on lab classes. That's what you're going to do your first lab tonight. I like to do lab work because when you do lab work, you learn by doing. And the best example I can give you is if you attempt to learn how to dry stick shift. I can promise you, somebody hands you a manual and says, here, read this and go dry stick shift. Or if you write down notes in a classroom, you're not going to be able to do it. They could sit you in a class like this and charge you lots of money for you to learn how to do it. It's not going to work. You learn a lot better when you learn by doing. Second reason I like to do a lot of lab work is that while you're doing lab, I can walk around to every single one of you. So if you're stuck on something, you don't get it, you don't have to sit there. All right, I'm right there to help you out. You get that? individual instruction. If you are going to school all day long, or if you're working all day long and you go to school at night, you know how exhausted you are this time of the day. All right? When you are actively engaged in your education and you're doing stuff and you're moving around, not only are you going to learn better, but time also passes a lot faster. So that's why I have every single one of my classes as hands-on lab classes. Okay? I'm going to give you the syllabus. The syllabus is considered to be a contract between yourself and myself, like the university. And what it means is that if you follow what's on here, you should be okay. If you choose not to, then you're probably not going to be okay. Now, about a year or so ago, the administration decided they wanted to dip their fingers into the classroom. And they decided they wanted the syllabus to be a certain way. And they said you have to have tons and tons and tons and tons of stuff in the syllabus. So when I took their templates, as it's called, it turned out that the syllabus was 7 pages long. Now, if I hand out a 7-page syllabus, I guarantee you, nobody's going to read that. I know somebody whose syllabus was 15 pages. That's a lot. So what I did is I took the required syllabus, and I don't know if it's available to you online yet. I sent it in maybe 2 weeks ago, so it should have already been posted. That's 7 pages long. I decided what I would do is take the syllabus and make it into one sheet of paper. So I just took out certain pieces of information, and I have it on here for you. It's two sides, okay, so 2 pages technically. And what I'm going to do is go over this syllabus with you. If you want the 7-page version, you are welcome to go view it online, or you can print it out if you choose. But I don't think that you really need to have from me a photocopy of Kane's symbol or different policies, because these are policies that everybody is giving out, so I give it out repeatedly. So everything that is most important is here for you. Right, all the way at the very top, I do have to point out to you that we do meet 2 times a week. That's why you end up getting 4 credits. Okay, just sign this. We are in this room all the time, T211, and class will start at 7:30 and go to 7:15. Right, it's a lab class, so that's why they put in that extra time. Now, if we finish earlier, I'm fine with that. I'm not going to make you stay. Right? I don't anticipate going beyond that time, right? 7:15, that's when class is over. If for some weird reason we don't finish everything that we need to finish, and that does happen from time to time, I'll stop right there and then we'll just continue and catch up the next night. So this what I gave you here is the shortened version. The first page gives you a nice data table. People who are science people really like data tables. In the first column, you see the day, and then next one you see the date. The next column, middle column, shows you the different topics that we're going to be doing that night. And I tried to make it as short as possible. I didn't want to go into lots and lots and lots of details for the topics that you're going to have in the class as it is. So these are the major topics. In the next column, I gave you the different page numbers from the book. All right, I will go over the book. All right, I'll explain a little bit, just a few. But I don't like to say, well, we're just doing chapter 1 today, chapter 2 the next time. I would rather give you very specific page numbers. And the reason is that sometimes I like to pull something from a different chapter into a different chapter. So for example, if you look here where it says these readings for introduction and Europe itself 4 through 16 and 656 to 661, it makes sense putting this stuff in here with that. That's why it's there. Okay? Now if you oh, I'm sorry, I forgot. I also have when the papers are due and when the exams are going to be due. Okay, so they're on there for you. I am very good at following the syllabus. If, for some weird reason, we end up having snow days, which I don't anticipate, usually I don't print out a brand new syllabus. It just doesn't make any sense. Usually when we have snow days, or I think last year we had shall I say, an incident day when the campus was shut down because somebody threatened that they were going to kill everybody. All right, we lost a day of education that day. We just play catch up, okay? Now, on the other side, I have the information about the textbook. All right, the information about the textbook, I have it one under 7. I have to go over certain pieces of information about the textbook with you. I do have a copy up here if you do need to look at it. I gave you the ISBN. It's listed here. But this is what I want to school. This is my meteorology textbook. And you can see that there is a sticker right there, because that's what they used to do. They used to put stickers on the book. And if you can see that sticker price, it says $15.95. Okay? That's when textbooks were really cheap. They didn't have the nice pretty pictures that they do. And they had a hardcover. That's why that book is still lasting. All right? I do understand that the books are extremely expensive and that your finances are very low, right? And I know something that's running through your head, and that's a question that I can't answer, because somebody already emailed me that question and I can't answer it directly, but I can kind of dance around it a little bit. I am supposed to tell you that it is a required textbook, okay? I would very strongly suggest you find some way of cutting down your expenses. That would be a very, very smart idea. If you're taking a course one time and you're spending well over $100 for a book, that's a lot of money. Maybe you can find a book really cheap somewhere. Maybe you can find an online version. Maybe you know somebody who has the book and you can borrow theirs. Or maybe you buy the same book with somebody else and share it. Right? Whatever you can do to cut down on the price would probably be a very smart idea. Okay? I don't know how much the textbook costs because as the instructor I get it for free. Okay? But I do know that they're expensive. So you have to decide what you have to do. I will tell you that I can't test you on what I haven't taught you. So you can all read between the lines. Okay? But I do have the book here. You can take a look if you need to. Now, as for attendance, Payne does have an attendance policy. And you're given a total of 3 cuts, but beyond that, then you start to lose some points. Okay, not a very good thing. If you're not in class, you don't learn material. I have 2 sign-in sheets that I will be passing around. The first one you already saw, and I'll pass it around when the class starts. And all you're going to do, once you get it, is just sign on the first available line. I'll be using this for a couple of days. So you sign here, just time it when you came in. Next person will sign here, time it, and so on. All right, that's the preliminary sign-in sheet. Then when it's time to leave, what I will be doing is giving you a different attendance sheet. Now this one here, you're going to sign in a little bit differently. There will be a little tiny piece of paper attached to this. It's my roster. I just have a little tiny strip of this. You're just going to find your name and your number, and then you'll just sign next to it. All right, so if your number is, let's say, 5, you would just sign there. This way, just in case something happens, and maybe I forget to give you the first sign-in sheet, well, I got you covered because I got you on the second. So there's going to be one to sign in and one to sign out. All right, that'll keep in my records. As for lab work, I have to put in something here just because I had somebody do something stupid one time. I did have a student who had some, shall I say, serious problems. And he sat there in class and he said, sat there with his arms crossed and he said, I'm not doing this. Okay, that's fine. He doesn't want to do his work, that's fine. He's an adult. He failed the class, then he made a big stink about it. All right? So he lost. He failed the class. All right? That's why I put in here, if you refuse to do your lab work, I cut your grade by 50%. This is called CYF. You don't know what that means, covered your you know what. Okay? Now, as for office hours, I would strongly suggest that you stick with emails or in person if you need to speak with me. You can catch me before class. Across the hall is a room called the Mac room. It's T218. So if you just go down the hall that way, you'll see it's the first door before, thank you, before you go to the stairs. I'm here, usually by about 4, and if that door is open, I'm here. Okay? So if you need to speak to me before class, you can find me there. I usually get in here between that time and 4:20, or I usually am bringing stuff in. Thank you. So I'll be back and forth between that room and this room. Or you can find me during break time, or you can speak to me after class if you choose. If you wish, you can leave a message with our secretary. I gave you the telephone number right here, but she'll put a message in my mailbox. I don't check my mailbox every day because I don't need to, because it's all the way up to the science building. Or you can put a message there in my mailbox if you choose to. If you choose to go there, this is what you have to do. You have to go all the way down the hall this way, all the way through the lobby, till you get to the water fountain, make a left turn, keep going all the way down to the end of the hallway till you see the hallway open up on the right side. When you go down that hallway, you'll see a periodic table show up in front of you. When you get to the periodic table, you have to make a left turn. Then you go to the next hallway, and it opens up on the right side. You go down that hallway, immediately up the stairs. By the time you get all the way to the top of the stairs, what you have to do is make a right turn, and that'll get to the SESS office. From here to there will probably take you a good 4 to 5 minutes of brisk walk. So I would suggest you just find me here. It's going to be so much easier. Or email. I do check my email, usually early evening. If you email me, you have to misspell my name, okay? I have 102 N's, and if you spell my name correctly, then it's not going to get to me, because Kane only allows 8 letters here. And I have asked them numerous times to correct it, all right? They won't correct it. So you have to purposely misspell my name in order to get to me, okay? I've had numerous students complain to me, you never emailed me back because I didn't get it. So I have it written right here for you, okay? I do always email back. It might not necessarily be that day. If you may email me, let's say after 8 o'clock at night, I'm not going to get it till the very next late afternoon, early evening. I don't have access to my email during the daytime. If you email me early in the morning, same thing. So I usually check my email late afternoon, early evening. Okay, let's say somewhere between 4 and 8 is when I'm doing that. So if you email me, you want a response, it's going to come right back at that point. Now, as for grading, I'm going to skip over university closings and items needed because those are pretty obvious. You're going to be graded by 5 things. I'll give you 3 exams and 2 papers. All right, I have the dates of them listed here. They're folded in there to make it nice and easy for you to see. I'm sorry, I think I'm the exams are multiple choice, matching true and false. And I hate to say short answer because that tends to suggest writing. You'll be putting down a word or 2 or a number. Okay, that's all it is. They are on Scantrons because that way I can throw them into the machine and they're done. And then the next day, what I will do is go through them and get the grade. So I'll have them all done and graded for you very, very rapidly. I do give study guides. Before you take your exams, I have study guides prepared for them, and I will give them to you ahead of time. I usually give them a week ahead of time. If you want them earlier, I can give it to you earlier. They're also on Google Drive, and I'll get back to that as well. The exams will count 50% of your grade. So you have 3 exams for half your grade. Okay? And what's nice about that is that when you have more exams, each one counts less. So if you're not really that good at taking exams, they don't hurt you as much. All right, I will be giving you 2 papers. These count half of your grade as well. So 2 papers will equal 3 exams. So you have a total of 5 grades. Please don't say, I didn't do well on that exam, can I retake it? I don't do that, that's not in the syllabus. Okay? Let's see. There are study guides, as I said, that are available to you. If you need extra help, and I'll come back to that, I will certainly give you extra help. I'm not going to give you the papers tonight. I will give them to you when we get closer to the time that is needed. Now, as for something that really irritates people who try to teach, if you're playing with a phone, you're not engaged in your education. Same thing with computers and those other tools, which means you're not going to learn anything. And then when you fail the exam and then say, can I retake it, that's just going to really piss off the teacher. Okay? So please restrict your cell phone use and all those other things that you play with. It'll fall away. Great time is a good time. And you will survive without them. Seriously, you will survive without them. Okay? Extra help is always available for you if you need it. Now, when I was at Rutgers, I had this one class called genetics, which should have been a really good course. The teacher did not make it a very good course. I went to him one day for extra help, and he actually said no. All I wanted was 10 minutes. He said no. And I wanted to say to him, who do you think you are? You're a teacher. You're supposed to be giving extra help. And I was a teacher at the time, so I knew. All right? Did not like that attitude at all. I give extra help if you need it. If you need the extra help, you can find me before class, break time, after class. I will stay with you if necessary. If you think that you need extra help for just a few minutes, anytime is fine. If you think you need extra help for a little bit longer, let's suppose you're really stuck on something and you know in your head it's going to take you at least a half hour, just please check with me and make sure that I can stay out, just in case. I don't anticipate problems, but nobody knows, okay? But extra help is always available for you. Now, as for what's called Google Drive access, if you go to your Google email for Kane, you can go to Google Drive. All right? I haven't done this yet because the last time I tried to do this, it did not work. I am not of the computer generation. You computers have issues with each other. You can, if you can get to Google Drive, once I think it's called Share It With You or something like that, you can get PDF files of all of the study guides as well as the labs. However, I have to scan the diagrams and things like that that are on the labs. So all I have available on Google Drive right now is just the text, just the questions that belong to the labs. And I'm not telling you to go home and print those out. You don't need to do that. All right, they're pushing that, but as far as I'm concerned, you're paying a lot of money to go here, and they should be able to accept a photocopy. So when it comes to labs, I will give you photocopies. If you really would prefer to have it on a screen because you like that much better, you can go to Google Drive and it will be there. I'm hoping that maybe this weekend I can get you into the position where I can share it with you, whatever that's called. Okay? They also put here the grading scale. I should point out that this grading scale is permitted. Every faculty member has a different grading scale. Okay? So this is the one that I use. This is the one that I like. Unfortunately, there are no A pluses. I wish there were. And I wish there were C minuses and B minuses, but they don't have those. All right? But this is what I will follow. So this is the 7-page syllabus, condensed, only 2. Is there anything there you just don't get? Is there anything that I need to clarify before we go on? No? I always have extra copies, just in case. So if you lose it, I will get you another copy. What we're going to do then is go into your first notes. And that is going to involve what's known as measurements. If you are one of those people that really understands this stuff, then just please bear with me. But as far as I'm concerned, because I'm the teacher, I have to make sure that every single one of you understands. So if I have to put something down really low, I will do so. And if you're up high, up here, you get it really well, that's fine. But if you don't understand the really basic stuff, and I give you something that's harder, then I'm not doing my job right. So we're going to be, tonight, looking at 2 major areas. One of them involves how we do different measurements and calculations that go along with those. And then the second thing we're going to do is take a look at where everything comes from. Okay? So that will be all of the, shall I say, first units. Now, when I go through all of these slides and so on, if I go a little too fast, if I have to go backwards, just let me know. First thing we'll take a look at involves measurements. Right? The system of measurement that you will be using in here is called the International System of Measurements. And this system of measurement was invented way, way, way back in the 1700s. It's called the International System, but it's abbreviated SI. And the reason it's abbreviated SI is because these 2 words are reversed in their language. Okay? They call it the System International. Way back during the 1700s, the French had this revolution where they thought it would be a good idea to redo everything. Right? They went around, I guess, burning buildings and doing all kinds of nasty things. They cut off the heads of people, especially if people were rich or of nobility or educated. And they said, now what we're going to do is fix everything, make it better. Okay? I'm not too sure how that makes it better, but that's what they decided to do. So one of the things that they wanted to do was to make a brand new measurement system. And this measurement system, they decided, was going to be based on 2 things. One of them was direct measurements of the earth, and the other one was water. The reason why they decided to do this is because they wanted a measurement system that made sense. And if you compare it to the system of measurement that we use, you can find that our system of measurement is actually kind of screwy. If you think of the foot, okay, our foots we now define as 12 inches long. But the foot was originally based on the length of the king's foot. If the king was this huge man, then the foot was longer. And if the king was a lot smaller, then it was shorter. So that meant that measurement was not always 12 inches, which makes no sense. If you think of pounds, God bless you. Pounds are abbreviated LBS, which makes no sense. We don't see an L and a B in pounds, but it's abbreviated that way. So these people said, let's make a system that makes a lot of sense. The first one, has to do with the Earth itself. Here's an untilted Earth, and here's the equator. They said the distance from the equator to the North Pole was 10 million units. And they said, let's make 1 unit this big. And that's how they defined what we eventually now call the meter. okay? They took that and they divided it into smaller pieces and they made bigger pieces out of it as well. They also decided to use water to base their measurements on. Why would that be so? Why would they use water? What's so special about water on the Earth?
It's more than land.
Yeah, there's a heck of a lot of it. Yeah, when you look at any globe, even this really old-fashioned one here, you can see there's a lot of blue there. So it makes sense basing the measurements on those two things. You don't need to copy this. I'm just showing you. Way back when Abe Lincoln was president, he was introduced to this measurement system. And he said, this is a good one. And we officially adopted it back then. But we don't use it because we don't like it. So I'm sorry. Then, in the 1970s, they did this push to get this system of measurement into the schools. They started to change the road signs. Delaware Water Gap, 37 miles, 60 kilometers. And it didn't really work very well, right? Because we don't like it. We don't understand it. It's not in our guts. But they did try to push this. There are a couple of reasons why this measurement system makes a lot of sense. And the first one is that it's based on decimals, just like our money is. If you think of our money, we have, I should have had a $1 bill here, but we have 10 pennies making up a dime and 10 dimes that make up a dollar. Okay? That makes sense. It's a decimal system, which means when you use this system of measurement, you don't have to use fractions. You don't have to figure out, well, I have to put in a fourth of a cup of this and an eighth of a cup of that, and that will serve 3 people, but I'm serving 18 people. You don't have to do all this weird math stuff. All you have to do is slide the decimal back and forth. So this system of measurement really caught the eye of the scientists because it's all based on decimals. Second is that based on decimals or the number 10 and water, this allows us to do something very unusual. If you have your own home and you get a water bill every 3 months, you are billed for the number of gallons of water that you use every 3 months. But they don't measure the number of gallons going into your house. You have a pipe, and they know the diameter of that pipe, and they know the linear feet, the number of feet of water that pass through that pipe. And they do this complex calculation that allows them to calculate the number of cubic feet of water that you use. Then they do another complex calculation to change it into gallons, and that's how they bill you. So that means you can go from feet to gallons. You can go from a distance to a volume measurement. We can do that very, very simply with the SI system of measurement. A milliliter of water, and I poured almost a milliliter here. I'm going to dump this out. That little bit is about a milliliter of water. It's a very small amount. That is equal to a centimeter this way, a cubic centimeter. And that is equal to the, I'll say weight, or the mass of 3 aspirin tablets. This means we can convert from length to volume to mass in this system of measurement really easily. Okay? If you try to do this in our system of measurement, it's a little bit more complicated. That's why scientists really like that system. You don't have to worry about the temperature to go through stuff like that, but it is a very simple process in this system. The third reason, oh, I'm sorry. I think I got 2, I'm sorry. Now, what they then did is they came out with a total of 3 separate endings, or at least 3 that we're going to be using. Okay, hopefully these look familiar to you. So I am going to go through them kind of rapidly, but if you haven't seen them for a while, at least you'll have them. And I made a nice little data table because science people like data tables. There are 3 endings that we're going to be using commonly in here: meters, liters, and grams. One of the ideas behind this system of measurement was to try to make the symbol the same as the unit, because it would make a lot of sense. Instead of using LBS for pounds, they should have used P, but they don't. They use P to represent density, even though it's circulativity, right? Or I'm sorry, not density, something else. I'm forgetting what it is. In any case, meters are symbolized with a little m, and they're used to measure length or distance, and we use meter sticks such as this or rulers. Okay, this would be almost the equivalent of the yardstick. The second of the endings is the liter. And this is abbreviated with a little L, and this is used to measure volume or space. And we use beakers, graduated cylinders. I just dumped the graduated cylinder. Okay, that's how we can measure volume. The third of the endings is the gram, and the gram is abbreviated with a little g, and it's used to measure mass, or sometimes we refer to that as weight, even though they're actually 2 different things. Mass is the amount of stuff in you. Weight is a measure of full of gravity. We use triple B balances as well as electronic balances. So you'll be using both of those balances in here. These three endings are all given the value 1. And they decided that they needed to take, for example, the meter, and then break it up into little pieces, just like when we take a yardstick. A yardstick ends right here with 36s. We can divide this into 3 equal pieces that we call feet. Right? We can take the meter stick and we can divide it into equal pieces as well. But we do this by tens because it makes more sense. So we have to take a look at the prefixes that go in front of each of these endings. And we're going to be working with those. We'll be able to use a data table I'm about to give you throughout any type of measurements. This makes it a little bit simpler. Okay, these are the 6 prefixes that we would commonly be using in here. Right, these prefixes are kilo, hecto, deca, deci, centi, and milli. These things here, these prefixes are not words. When you hear the cops on TV say, oh yeah, we busted them for 3 kilos, they can't speak that way, even though they do. There is no such thing as a kilo. It's a kilogram, or a kilometer, or a kiloliter. These prefixes have to be in front of something. They can be in front of meter, liter, or gram, or something else. Okay? And I'll come back to that. They decided to abbreviate each of these prefixes using the first letter, which makes sense. Right, so kilo is a little k, hecto a little h, deca a little dk. And they wanted small letters. Meter, liter, and gram are still stuck here in the middle. And then as we go to the right, deci is a little d, centi a little c, milli a little m. Now in our country, when they first started to push this into the schools, they were making these abbreviations. They tried to make them with script letters. The problem is that at that point, this is before computers. Right? Most typewriters did not have script on them. So in our country, when you take a look at, let's say, a soda bottle, you'll see that liter is abbreviated with a capital L, because a little l, small l, looks too much like the number 1. So they tend not to use that. So we deviate from the pattern. Now the next shows you what each prefix actually means. We give meter, liter, and gram the value of 1, because this is 1 meters, so just call it 1. Right? 1 gram would be 3 aspirin tablets. 1 liter, picture a liter bottle of soda. Okay? The prefix kilo means 1,000. So this is why you cannot, you cannot use kilo all by itself. It's got to be attached to something. If I had, say, for example, $1,000 in my pocket, I could technically say I have a kilo dollar. It sounds stupid, but that's correct. Anytime you see kilo, it literally means 1,000. So we can put kilo in front of meter, liter, or gram. I'm going to stick with meter just because I happen to have a meter stick. If I have 1,000 of these together, end to end, that's a kilometer. Hecto means 100. So if I have 100 of these, that would be a hectometer. Deca, if you think of the word decade, is what number?
10.
Okay, so deca means 10. Now, one problem that we have with deca is that it starts with a D, and deci starts with a D also. That's why they had to throw that K there. But if you just remember decade, then it's going to make sense. All right, so please notice the pattern. All right, we're going by tens. And that's what makes this system so useful to us, especially when we start to convert. Deci is 1/10 of a meter, liter, or gram. On this meter stick, a decimeter is from the edge to the number 10. So it's about as wide as my fist, or from the 10 to the 20, or from the 20 to the 30, and so on. Okay? Centi, well, you know there are 100 cents in a dollar, means 1/100 of a meter, liter, or gram. A centimeter is about as wide as my finger. So these littler numbers that you see over here are all centimeters, and there's a total of 100 on here. And then if you just continue the pattern, milli means 1,000 of a meter, liter, or gram. There are little tiny itty bitty lines that look like eyelashes on here. Those are millimeters. Okay, they're very, very tiny. There are 1,000 on here. You're welcome to count them if you wish, but there are 1,000. This chart is very nice because this is going to allow you to very easily convert, and you don't have to try to remember different values. Now, when the scientists came out with this system, they came out with all of these prefixes, and there are bigger ones and smaller ones. If you take a medication, you might take micrograms of something. You might be familiar with gigawatts of energy and so on. They're much bigger, much smaller. When they came out with this system and presented it to the scientists all over the world, everybody was really thrilled with it. And they decided that they would use it. But there was one problem. When they originally measured the distance from the equator to the North Pole, they measured it wrong. So that threw everything off. They originally called this system of measurement the measurement system. This is called the metric system. That's what that term means. And then when they found they made a mistake and they went back and they changed it a little bit, they corrected it, they decided to change the name. So they changed the name to the International System of Measurements. It's abbreviated IS. I'm sorry, SI. Excuse me. So that's where the name actually comes from. I'm going to give you a couple of sample problems. If you understand them, just please bear with me. If you don't get them, I will be giving you a homework photocopy, and it's absolutely optional. You don't have to do it. But if you are the type of person who needs the practice, I'm giving you the practice. It's up to you. So when I give you the homework assignment, the homework paper, if you do it, that's fine. Next class, I'll go over it with you. I'm going to show you how the system is so easy when we have to convert something. If you think of this number 2 here as $2, you could write 2.00, and there would be an invisible decimal point here. Right? You don't have to write that because everybody knows that it's there. In any case, we're going to convert 2 centimeters into millimeters. So there's an invisible decimal point, which I can't draw on here. All right, we're going to go from centi over to milli. So if we start where centi is and we go over to milli, we're just taking one step to the right. And do the same thing with the decimal point. All you have to do is take this invisible decimal point right here and move it one place to the right, which is the same thing as saying multiply by 10. So this number becomes 20. The decimal point is here, and move it one place to the right. That's all you have to do to convert. Right? So it's one example. The second example, we're going to go from 3,000 milliliters and change this into liters. So if we're starting with milli, and we're going to go to liters, we're starting here, we're going to go all the way over here. In order to do so, you stand here, don't count displacement. You stand here, you go 1, 2, 3 places over to the left. We're going to take this decimal point, which is right here, move it 3 places to the left. When we move it 3 places to the left, it becomes 3. Right? The third example, we're going to change 5 kilograms into grams. So here's kilo way over here. We're going to change it to grams. What direction are we going to move the decimal? The right or the left? The right. We're going to move it to here, so we're moving it to the right. And now we just have to count the number of places we're standing here, so don't count it. 1, 2, 3 places. The decimal point is here. We can move it 1 place, it's 5. 2 places, it's 50. 3 places, it's 500. So you don't have to sit there and think, well, kilo means this, and hecto means that. All you have to do is just count. Really, really simple. Decagrams, 4 decagrams. We're going to go from decagrams to decigrams. So which way are we going to move the decimal? To the right. How many places? 2 places. You're standing on deca, so you don't count it. You're going to go 2 places over to the right, and now it becomes 400. The decimal point was here, 2 places to the right. Same thing as saying multiply by 100, because since this is a decimal system, each of those boxes is 10 points more or less. Now, here's where people get confused. This is the abbreviation M, because meter is abbreviated M, and milli is also abbreviated M. So a lot of people look at that and say, well, which one is it? And all you have to remember is this. These prefixes cannot exist by themselves. So if you see an M all by itself, it has to be meter. Because milli has to be attached to something, either meter, liter, or gram, or seconds, or jumps, or something, whatever. It has to be attached to something. So we're going to go from meters to hectometers. So which way are we moving the decimal?
Left.
To the left. How many places?
2.
2 places. So 7,000 becomes 70. Just move it 2 places to the left. It's here. Okay? And I will give you one more. So I'm giving you 6 different examples. If you get it, that's great. If you don't, let me know and I will help you out. We're going from 1 liter and we're going to go to milliliters. So which way are we moving the decimal? To the right. How many places?
3.
3 places. It's the same thing as saying 10 10, 100, 1,000. Okay, we're just multiplying by 1,000, moving three places per day. So it's a really easy system of measurement to work with. Most of us who were born in this country don't have it in our gut. So if somebody says to you, I just walked 2 kilometers, you're going to say, I have no idea how much that is. But it is a very logical system. All scientists all over the world use it. A second thing that we're going to look at before we see where everything comes from involves what's called unit conversion method, or the factor label method. This is actually a very simple, if not slightly tedious way of converting one type of unit to something else. If you look at these two people standing here, there is a crystal right there. That's a crystal called spodumene. And this is telling you that this crystal is 12.2 meters long. That's pretty long. And it weighs 8 tons. Now, I drive a subcompact car. It weighs slightly more than 1 ton, more than 2,000 pounds. So I know that that in itself is 4 my cars. That makes sense to me. If I wanted to change tons into pounds, I could do that pretty easily. Right? You could probably do that in your head, because most people know that 1 ton is 2,000 pounds. But there are some other measurements people really don't have in their heads. And it's easy if you have a very simple method that will show you how to convert. So this is the method we're going to take a look at. In order to do these conversions, what you do is you write the original number here, 8 tons, because when it changes into pounds. And then what you have to do is multiply that number by some fraction. That's what you see over here. That's called a conversion. In case you haven't heard these terms for quite some time, numerator, denominator, top number, bottom number. Since tons is up here, the top number or the numerator, you have to put tons down here. Because this is going to allow tons to cancel out, they divide out. And then all you have to do is know what that conversion is. So 1 ton is 2,000 pounds. Or we could pronounce it 2,000 pounds per ton. So tons will cancel out. And all we have to do is multiply 8 times 2 and get 16,000 pounds. Okay, it's a very simple way of converting. This is a practice that's used in chemistry and physics a great deal because it makes sense. It's a very simple thing to do. I just gave you a one-step conversion. It's not always going to be that simple. You just have to make sure that whatever the original number is, you write down the units, you put that same unit down below. Okay, so the top here, it goes down below here. I'm going to show you a two-step problem. Can I move this? Anybody need it? And on the homework sheet I will give you, there are some practice problems there. Okay, and if you still don't get it, let me know and I'll help you out with this. Next we're going to do is take that spodumene crystal at 12.2 meters. That means 12 of these sticks and a little bit more. And we're going to change it into feet so it makes some sense. But it's a two-step problem. Okay. That's what spodumene is. Very good. Okay. You write the original number, which is 12.2 meters. And that's going to be multiplied by a fraction. Meters is up here at the top. This is actually over 1. Okay, so meters has to be down here. Okay, you might not have it in your head that a meter stick is 39.37 inches. That's something that's in my head. I don't expect you to know that. So if you had to convert something, I would give it to you. Okay, you don't have to worry about memorizing things like that, because memorizing stuff like that is really useless unless you use it all the time and eventually sticks. So 1 meter is 39.37 inches. Meters will cancel out. But this is going to put the answer in inches, but we have to put it into feet, which means we then have to multiply this by a second fraction. Here's the second fraction. Since inches is up here, we need to put inches here. And most people know that 1 foot is 12 inches. If you don't, let me know, and I will tell you that. So we put 12 inches down at the bottom, 1 foot is at the top. So meters originally cancels out, inches will cancel out, and then the answer will then be in feet, which is what we're looking for. So you would take your calculator, and sorry, I'm going to say this anyway. You will multiply 12.2, multiply 39.37, it equals divided by 12 to get your answer. Okay? So this is a multiple step problem. It's a little tedious setting that stuff up, But if you do this method, you don't have to sit and go into your head and try to decide whether you're going to multiply or divide. Okay? So it's a method that is very, very useful to us. You will be using this from time to time. Okay? If you don't get it, you're just going to let me know. Switch. Waiting. Let me make this a little bit darker. We're going to take a look at where everything came from. We're going to turn this really dark for a moment. Can you see two dots?
Yes.
It's like an iPad. The big one that you see is the Earth. And you hopefully can see something right there maybe. That's the moon. This is an actual photograph. This is called the Earth-Moon system. This is a gorgeous picture. The Earth, the photograph was taken from a satellite going around the Earth. So that means the satellite is fairly far away. So if you take a look at that, you'll notice that there's nothing surrounding us. Outer space is black. There is nothing there. Everything that we need to survive is on our little Earth. And our Earth is very tiny compared to everything. So we're going to take a look at a number of reasons as to why we study a topic called geology. We really have not been able to figure out why the Earth has everything that we need, or at least scientifically. We know that the Earth is the only planet that has life on it that we know of. People have sent robots to certain other planets. They've attempted to look for life, haven't been able to find it. They've recently shifted their attention to looking at some moons, still can't find it. So we know that the Earth is the only place where life, as we understand life today, can exist. Earth is in what's called a habitable zone. And the habitable zone is probably best understood if you think of Goldilocks and the Three Bears. You know, when she got to the porridge, it was just right. It happens to be in the just right place. Because of the distance from the sun, our temperature and pressure are just right. We're 93 million miles away on average. So the temperature and pressure are just right. We have a whole bunch of liquid water covering the surface. Almost 75% of the surface of the Earth is covered by liquid water. The reason why water is important is because water is the universal solvent. That means it can dissolve anything, given enough time. Water will dissolve food and bring it into cells. The cells will use it. And then water will dissolve waste and take it out of cells. Okay? It allows things to move around. We assume that because all life on the Earth needs water, that only a planet or a moon with water would have life. That's an assumption we have to make. Okay? We have a breathable atmosphere that allows us for a gas exchange and so on. So everything that we need is sitting right here. Why? We don't know. Maybe because we just happen to be sitting there. Okay? When we take a look at all of the other planets, none of them are in the habitable zone. The habitable zone extends roughly around here. Okay? But none of the other planets seem to have the required stuff. Number two has to do with building supplies. There are building supplies such as the rocks that you see that make that beautiful stone fence. We can go to different quarries, such as a marble quarry, and we can cut that stuff out and shape it so we have beautiful statues or floor tiles. We can go to certain other quarries where we can get slate, which is very, very commonly used. Slate can be found on the older blackboards, not the green boards that we now have. We can find it as patio stones, very commonly used for roofs and so on. And earthquake-proof structures, which is almost a joke. Right? There's no really such thing as this. There are certain places where they are trying to build earthquake-proof structures, but sometimes an earthquake occurs and the building collapses. So we can't quite make them the way we want to at this point. Third reason why we study geology is that it contains the history of life as well as the history of the Earth in the rocks. And so far, based on what we have seen, we are incredibly unique. Okay? We have very nice fossils inside of the rocks that we take out, and that tells us a little bit about what life was like in the past. We can analyze the chemistry of different rocks, and that tells us what things were like in the past. We can look for where there have been impacts, and when there are impacts, meteorite impacts, we know that stuff came in from outer space. This is what we use to try to figure out what the past was like. You might be familiar a couple of years ago with the Martian meteorite from Allen Hills in Antarctica. They discovered a meteorite, and they found this strangely shaped object right here. It looks very, very, very much like a bacterium. So they thought, could this be proof that there was life on Mars? They studied this, and it turns out that it was just a natural accretion. Okay, so at this point, they haven't found life on Mars. They think that Mars can't have life because it gets hit with too much UV radiation. So they haven't discovered any at this point. Number 4 involves economic reasons. There are various minerals that we certainly need in order to survive. This is a very pretty mineral. It's named after a fruit. What fruit?
Watermelon.
It's called watermelon tourmaline. Very pretty mineral. There are various fuels that we need. In the background, that's a coal seam. Coal is something that we have a lot of in this country. If we didn't have air pollution laws, we would have no problem burning all that coal. We would have no energy crisis.
Where can you find the watermelon
Tourmaline?
yeah.
Usually the gems are associated with metamorphic activity. So you'd have to go to a place where there's probably some volcanic activity or some intense squeezing of rocks and find it in there. I don't think we have any in New Jersey. Not to my knowledge, sorry. We have other things in New Jersey, what can I say? Over here, you're taking a look at something I can't bring into the classroom because this is toxic. This is called petroleum oil, if you want to call it that. It's a toxic substance. Also, we have to worry about toxic wastes. We have quite a lot of that here in New Jersey. We have to be able to dispose of this safely, and we haven't. There was just an article in the Star Ledger, just a couple of months ago. Chemical Control Corporation in Elizabeth is still dirty, and that blew up in the 80s, 1980s. Right? We have to find places where we can store toxic waste as well as radioactive waste. And I really hope that this is a mock-up picture because nobody in the right mind would stay next to that stuff. Okay? But we use geology to find places where that can be, where they can be put. Number 5 has to do with geologic hazards, also called geohazards. You are certainly familiar with the earthquake that hit in Italy. Right? That was, I think, 6.2 on the Richter scale. Last thing I heard, there were about 300 people that were killed. Right? I assume that number is going to keep going up. We do get earthquakes here in New Jersey. For the most part, they are not that severe because we're not in earthquake zone. We have volcanic activity. At the present time, we do not have volcanic activity in New Jersey. We did in the past a number of times. There are a lot of places in New Jersey that show volcanically formed rocks. We actually do have an ancient volcano in New Jersey. That volcano is so old. It goes way back before the dinosaurs were even born. It's never going to erupt again. We'll take a look at that later on. But we have to find places where we can get people safer because of all of these things. Whether it would be landslides and so on. This is some dumb thing that humans do. We build houses at the base of a mountain that can easily fall down. What we need to do is identify places where we can have landslides to keep people from building there. Okay? That would be very smart. Number 6 has to do with different food supplies. We have, let's see, I think the number is around 2%. We have enough food to feed everybody on this planet. I think we have 2% more than we need. The problem is getting them the food. We can't just put the food in any place. There are certain places where they've gone into deserts. And they've had this ridiculous idea, oh, all they have to do is plant seeds and put a lot of water, we'll be fine. Deserts don't have enough organic material. The minerals that are in what are known as trace minerals, that means they're in very small amounts, are in the soil, and the plants use them. If you go to the grocery store and you buy those beautiful red tomatoes that are about the size of my fist, I believe they're called tomatoes on the vine, they look gorgeous, they don't taste that good. If you get a tomato from out here, this area of New Jersey, I guarantee you, all tomatoes, whoever tastes after that will never taste as good. Because what we have in our soil, and different trace minerals that are in our soil, give our tomatoes a really characteristic taste that they have. That's going to allow us to be able to have very, very good tasting food. Okay? Number 7, geology relates to and complements the other sciences. For example, these are some dinosaur footprints, trackways. What we can do is use physics and measure the distance between them to eventually work out whether they ran or walked. We can use a little bit of biology to determine what the ancient reptiles were like. What you're looking at here is called a maleo bird. This is the only bird that digs into the soil and lays its eggs and buries it. Reptiles do that. So we can use them to figure out what maybe the reptiles used to do years ago. There are certain chemicals that can be mixed together, and when they mix together, they take on a spherical cell shape. This is not a cell, but something similar to it. And things are found inside of it, just like in cells. So we can use chemistry in order to, as well as biology, in order to figure out where life came from. We use chemistry to test soils, so we can determine whether those soils are safe to build on, get food from, and so on. Okay? This brings us to what geology is. This is a definition for geology. The study of 3 things: composition, structure, and history of the earth. Okay, all 3 of those things are covered in geology. This goes back to approximately 250 years ago. Hutton and Lyell are considered to be the founders of geology. They put it all together, and Lyell wrote the first book, if I remember correctly, on geology. This is considered to be a fairly known science. We take geology and we subdivide it into 2 classifications. One of them is physical geology. Okay, physical geology means we study the rocks and minerals and the different processes that carve our planets. They can be on the inside, they can be on the outside. All of that is known as physical geology. The second subdivision is referred to as historical geology. And with historical geology, with historical geology, we study the origin and evolution of the planet itself. That allows us to look at the continents, what they were like way, way back in time, what they're going to do in the future. Allow us to look at the air. The reason why I have a picture of a volcano is because volcanoes produce our air or atmosphere. They also produce the ocean. Okay? And we also take a look at the living things going way, way, way back then as well. All of those are covered under what is known as historical geology. When we look way back in time, we can find creatures that look sort of like us, but not completely. If you look at this ancient hominid, notice the bump on top of the head, that little crest, and look at those huge eyebrows. That's all bony material. We can use biology to put a face on that. So those are the 2 subdivisions. As for the major ideas, okay, the first one is that that geology is an extremely, extremely, extremely young science. Only about 250 years old or so. When we take a look at chem and physics, they go back 2,000 years. They are a heck of a lot older. We can think of geology as sort of the biochemistry that's going on today, where they're doing all kinds of very quick ideas in a very short time. That's what geology is like. Right? Number 2 has a huge number of incredible ideas in only a very, very, very short time. I'm going to show you a list of some of these ideas. I'm not going to ask you about them. I'm just going to show you that I want to give you a couple of examples. Okay? These are just some examples. People used to think that volcanoes were mountains that turned into volcanoes. Okay? People did not know that they built themselves. They had no idea that continents could move around. They thought that living things in the past had always been the same. And many years ago, when they found these gigantic footprints that looked like birds, they said they were just giant birds. Now we know them as dinosaurs. So there are a whole bunch of reasons, a whole bunch of examples, I'm saying. Number 3 is the most important one. The concept of time has changed. In geology, they were able to introduce Millions and billions. These are things that we do not understand. A normal human being cannot understand. Think of the national debt. We can't understand that. Okay? Before geology, the Earth was considered to be very young, just a couple of thousand years old for the most part, and the biologists couldn't work with it because they could not explain the changes that saw in living things over such a very short time. And when geology introduced the concept of millions and billions, the biologists were very, very happy. It allowed them the time that they needed to see how things could change over time. Right? The picture on the left is supposed to be $1 million. The one on the right is supposed to be $1 billion. I don't know. Right? Those are concepts that are very foreign to me. They try to make time a little bit more understandable by making it look like a clock. If this is where the Earth forms, all of this time here, 24 hours, is supposed to be all the time that has existed. Right here is when the dinosaurs died out, and right here would be the present time. It's a little hard to understand. All right, you don't have to know these, I'm just going to show you these. These are some estimates that different cultures or religions came out with to try to explain how old the Earth is. And you'll notice that the numbers are very, very, very young. The oldest one, the Hindus, is 13 million. Scientists today believe it's 4.6 billion years old. There's a big difference there. Okay? There was a very famous person, Archbishop Usher, who went into the Bible and he looked at the begats. Adam and Eve begat or had these children, and he assumed that one begat was 20 years, one generation. He estimated when the Earth was formed. He said, based on the number of begats, it was made on October 23rd, 4000 BC. Then there was another person who I think worked indirectly with him, who then said, and it was created at 9 o'clock in the morning on a Friday. I'm not too sure how he came out with that. But this is what people thought. When we take a time that is that young, roughly 6,000 years old, it doesn't fit with living things and how they've changed over time. There are certain calculations that we can do to show us that this time would be too short. So that's why the scientists were very, very happy when geologists came out with the Earth being a heck of a lot older. Okay? The fourth of the major ideas was that the rocks and the sediments and the fossils tell us all about the history of the Earth. And the important thing is for us to learn to interpret them. When we take a look at this rock, for example, that says that was a landslide at one time. The rock tells us there was a landslide there. When we take a look at this tells us that there was a fast-moving stream here. There might not be one there now, but you could wait a little while, you'd probably find one there. When we take a look at these, we can tell way back in time there was a really, really nasty creature called T-Rex, much bigger than a human being. That head is 4 feet long. That means more than a meter thick. Okay, huge. We know that that creature was on the Earth. At one time they thought it was a stupid lumbering beast. They reinvented it to being a little bit faster. They don't think it ran, but it maybe could have. We have to learn how to interpret that. Okay? This creature here is something that we have no idea what it is. We can't classify it because there are no modern counterparts. So this is something that people are attempting to try to understand, but we can't at this point. Right? So literally, all of what's about the Earth is written in stone, and we have to learn how to interpret that. I'm going to give you an example of an interpretation. You take a look at this, you can see footprints from a cat, and then all around here and over here, you can see footprints from birds, or one or two, a little hard to tell. Okay? When we take a look here, you can see they cross each other. So, what would be the relationship between the cat and the birds in this picture? How are they related? What would be your guess? What would the cat have done? Yeah, chase it and then ate it. That would make sense. Okay? That would be a very, very good interpretation. That's what we tend to do in geology. We tend to interpret things. When we look at tracks, we can use that to interpret stuff. However, I took these pictures, and I know that didn't happen because the bird prints were there. I came home, this is my front yard, and when I went onto my steps, I saw a stray cat walk across my yard. So what happened is that the birds were just jumping around here, probably looking for food. They left all of their footprints. Later on, I don't know how much later, but later on, the cat walked through there. So it's a reasonable interpretation, but it can be wrong. Sometimes that happens. Okay? Yeah, we're going to come back to that. What we're going to do is take a 10-minute break. When we come back in 10 minutes, we're going to take a look at where everything came from. The bathrooms are usually down there, but both of them are shut. Okay? I don't know if the bathrooms are open downstairs. The other bathrooms, if you go in this direction down the end of the hall, when you go through the lobby, make a left turn, because you can't really go in any other place, and you'll see the bathrooms are on the right side. Okay? Past the water fountain. None of the water fountains are working on this floor. I don't know if any are working downstairs. Okay? If you need the candy machine, go this way. When you get to the exit sign, go all the way down the stairs. When you get to the end of the stairs, go through the double doors, make a right, go through the doors, and you'll see the candy machine. Okay? Let's start. Point was nothing more than a ball of energy. But as I said, where it came from can't be defined. Now, when it blew up, you have to understand this is before there were atoms and molecules. This is before light, before planets, and so on. Okay? There was nothing. Just this big ball of energy. Now, after it blew up, what happened was that it started to spread, as you can see like this. Now, this stuff in the background, I should point out these are not stars. God bless you. The dark stuff in the background, which is really nothing, they call elon. They don't know what it was. They can't tell where it came from, but it spread. Right? This ball of energy, when it blew up, spread. Now, as it spread, this allowed it to cool down. And as it started to cool down, things that we would call subatomic particles started to form. And then those subatomic particles then started to clump together to make atoms, and so on. Okay? Um, they have calculated, and I'm not too sure how, but they have calculated that after 60 seconds from when that thing blew up, that's when the atoms finally formed. So before that, there were no atoms. Now, people who are called cosmologists, these are people who tend to study astronomy and the stuff way before this, have come out with lots of details of what happens every couple of seconds. But as I said, I don't know where they got that information from. Eventually, atoms formed, and then they joined together to make what we call molecules, compounds, and eventually, here we are. Okay? That's very simply what the Big Bang Theory states. Now, the problem with theories is that they are not considered to be acceptable because they have to have evidence, until they have evidence that supports them. So we're going to look at some of the supporting evidence for this thing called the Big Bang Theory. There are three pieces of evidence that support the theory. Okay? And in order to understand that, what I want you to do is think of when you were a little kid and you were learning to write. The first thing you had to do was to learn that pen or a pencil had to be manipulated so you could hold it. Okay, that's the first thing you had to do. But once you were able to do that, you then learned that you could manipulate it to make letters. And those letters could eventually join together to make all kinds of things, such as notes to somebody, and then eventually, in time, all of that writing could give you your doctoral dissertation, whatever. Okay? You had to learn those steps. In astronomy, there is an instrument that's called a spectroscope. And a spectroscope is attached to a telescope. I'm going to pass around the spectroscope because I lost one of my briefcase here. This is what a spectroscope is. This is just a little cheap one. It has, at one end, a slit. The whole purpose of the slit is to cut down on the amount of light that goes in the tube. Okay, it's like covering one eye. The other end has a circle, and there's a piece of plastic there that has 5,000 scratches on it. If you hold it like this, you can just barely see them. What you do is you put the round part towards your eye, and you look up at the light, and you might have to rotate it. Don't look through it, because this is not a telescope. You look on the inside, okay? So you have to look at the edge here or the edge over here. But if you do this, you'll see what a spectroscope does, okay? So the slit goes to the light. When the spectroscope is working, it behaves just like a prism. And a prism takes what we call white light and bends it open. Just like when you take a book and you bend it open. And that allows you to see what we call the rainbow colors. Now, the rainbow colors are officially called the spectrum, so you're going to hear me say that word. This spectroscope can be attached to a telescope, and we can aim it at stars. And when we aim it at stars, this gives us a lot of information. If we have a source of light that shows us all the rainbow colors, as you see over here, they all blend in very nicely with each other. If we have pure elements, elements are these things on the periodic table, and heat them very much in the lab, they give off only certain colors, not all the rainbow colors. This one, I can't read this, but I think that says sodium, has that color. This is mercury, only has those colors. This is lithium, it only has those colors. There's one over here, and hydrogen has these colors. Every single element has its own characteristic colors when we heat them in a lab and look at them through a spectroscope. Okay? You can think of these better yet, think of these elements as the letters that you had to learn to write when you were little kids. Okay? When we take a look at a spectroscope through the telescope, what we find is that there is a huge amount of the simplest letters, so to speak, or hydrogen and helium. This is what hydrogen looks like, and this is what helium looks like. These are the simplest atoms possible. Just like you can take all of the letters and put them together to make words, these elements, if they're forced together to make other elements, okay, there are approximately 90 natural elements. Thus, the others are all artificial. They have to be made somehow. When we take a look deeply in space, what we find out is almost the entire universe is made out of only these two very simple letters. Okay? Hydrogen and helium. I'm going to show you what these look like. These are very simple atoms with very common letters. On the left, go back. I switch. Green. On the left is hydrogen. Notice how simple it is. One proton, one electron. This is helium. Two protons, two neutrons, two electrons. This is uranium. So these would be the letters that you're writing, and this would be a paragraph. Okay, think of it like that. Now the next piece of evidence has a lot of background behind it. Let's suppose you're in a car, and you're at a stoplight, and there is an ambulance next to you, and they turn the siren on, but they're not moving. You're going to hear the sound waves hitting you, and you're going to hear a certain pitch. Light does the same thing. If I have a really hot light, and I look at that light in a lab and it's not moving through a spectroscope, it might have those black lines in this particular pattern. Black lines just mean that those wavelengths are missing. Just like if I put my hand on if I cover up the word with my hand, you can't see the word rest. Okay? So look at those right there. Those are the reference lines. If we have that siren now heading toward you, as it moves toward you, those sound waves are going to get squished together, and they're going to hit you faster because it's moving toward you. What happens to the pitch of a siren as it moves toward you? Does the pitch go up and get squeakier, or does it go down and get lower? It goes up, it gets squeakier. All right, that's what happens with sound. You can hear that. Same thing happens with light. Notice where these lines were originally? Well, they're not in the same position now. Okay? They have, I'm sorry, this is where the lines were originally. This shows you they've shifted over to the blue side. They call that a blue shift because they're heading in that direction. If we have the ambulance instead moving away from us, you'll notice that these same lines here have now shifted over to the red end. So when you're at the light and the ambulance is approaching you, you first hear those sound waves squish together and it's high pitched. Then they move away and you have fewer waves hitting your eardrums every second. Right? With the light waves, we get exactly the same thing. When it moves away from you, you get a red shift. So same thing on the left side. Here you see the car, it's moving toward you, the waves squish together, moving away from you, they spread apart. All right, this is something you're actually very familiar with. When you are on the parkway and you see somebody aiming a gun at you like that, what they're doing is sending a radar beam to your car. We know what the speed of radiation is, speed of light. Okay, radar travels at the speed of light. Right? The radar leaves the gun, it hits your car, and it comes back. And then the cops can measure how fast you're traveling. So if you're traveling a lot faster than you should be, it takes longer for the radar to hit you and then come back. That's how they can tell at your speed. This is the same idea. All right, when we're tracking storms, this shows you some hail. We can use radar to track that. We can also see the hook on radar that shows us that we have a tornado. And we can actually see a rotation in the clouds based on this. When we take a look at the sun, we get the same exact thing. When we look at the sun through the telescope, the right side over here shows us a red shift, and the left side here shows us a blue shift. What that means is that this side is moving away from us, and this side is moving toward us, or in other words, the sun is turning on its axis. It's rotating. It's turning around like this. Okay? All of that is something that's called the red shift, or Doppler shift, or the Doppler effect. It's named after Johann Christian Doppler. This effect was very important in showing us what the universe is doing. When we take a look at almost every single star and almost every single galaxy, almost every single one of them shows a red shift. And because almost all of them show us a red shift, this tells us that the universe is actually expanding. Okay? That means the universe is growing. You can't go outside and see them moving. You can't take a photograph and see the stuff later on moving because the universe is just too large. But when you use the spectroscope attached to the telescope, that's what we can pick up. Okay? Now, this shows you some very bright light in a lab, and you're looking at that reference line right there. Here is a star, and you can see that this reference line has shifted over toward the red end. These are different galaxies at different distances. These are further away. Notice how far toward the red end that has shifted. So we can actually use this to actually work out the speed. Not everybody agrees with the speed of expansion of this thing, right? If you put some marks on a balloon and then you blow it up, they're going to spread. That's exactly what's happening with the universe. Now, the Doppler shift, and you don't have to know this, so I'm not going to ask you this. The Doppler shift is supporting the Big Bang Theory, but it also supports other theories. There's another theory called the oscillating theory that says the universe was together, it blew up, it's going to come back together again. Steady state theory says the universe has always been expanding, it's always going to continue to expand. So that doesn't narrow it down as well as we would like. The third piece of evidence that supports the Big Bang Theory, believe it or not, was discovered right here in Jersey. Right, there's a place called Bell Labs. These two guys here, Penzias and Wilson, had what's called a Horn telescope. That's that device you see in the back. They had this at Bell Labs in Holmdel, and as I understand, it's now closed down. They took this telescope, and it's not the same telescope that you would look through. It's a different type of telescope, but they aimed it in different positions. Just like when you see a sign that shows you different cities are in different places. They took the telescope and they aimed it in that direction, and they picked up a certain brand of radiation. Then they aimed it over here, picked up the same brand of radiation. Aimed it over here, picked up the same thing. And I'm going to give you an analogy. Let's suppose you go home and you turn on the TV set, and you see channel 2. You change it from channel 2 to channel 4, but you still see channel 2. Then you change it to channel 5, and you still see channel 2. Every time you change the channel, you get the same thing. Okay, that tells us something wrong is going on. So they said, something must be wrong with the telescope. They climbed into the telescope, and they found that pigeons were nesting. And pigeons make a big mess. So they cleaned all the pigeons out, thinking that that was really screwing up their results. And they got the same results. Then they said something's wrong with their calculations. They went back and they checked them, they got the same results. At that point, they decided that what they did was right. Now, suppose you go into a room and there are no pictures on the wall, it's a brand new apartment. When you walk through that room, what do you notice? What do you hear? You hear an echo, okay? Just like if you go to a well and you scream down the well, you're going to hear an echo. Just like bats will send out clicks or screeches, and they're going to bounce off the insect, and they're going to pick up that echo. Well, that's what this was showing us. When they took that horn telescope and they aimed it all over the place, they were getting number 3. This is an echo of the Big Bang explosion. This was considered to be a real big one. But you have to understand this is not a sound echo, it's a radiation echo. They're not hearing anything. The idea was that that original ball blew up, and that radiation has just been bouncing around in outer space. You have to understand that in outer space there was no friction, so there's nothing to slow it down. So they picked up this brand of radiation. The wavelength is 1.87 millimeters. These are microwaves. Yes, you cook with microwaves, same idea. Okay, microwaves, radar, almost the same thing. So this was considered the third piece of evidence that supported the Big Bang Theory because this is the echo of the explosion. This picture that you see over here is kind of a weird looking picture. This is supposed to be the microwave radiation turned into visible radiation so you can see it. So that's a photograph of the entire universe that we can see. This does not mean, don't get confused, we are not here and it's not this shape. This is just all that we can see. Now what that picture is supposed to show us, I have no clue. Okay? It's just supposed to show us what the universe looks like based on microwave radiation. Okay? So this is the third piece of evidence that supported that. There is a big problem with this theory, however. Okay? And see if this makes sense to you. If everything was together at a point, and then it blew up, and everything's moving away, how in the world did those subatomic particles come together to make atoms? That's something that they're having a little trouble with. We can't explain why matter or stuff clumped together because it's spreading apart. That's the sticking point of the Big Bang Theory. If everything is spreading away from each other, somehow it had to come around. So let me give you an analogy. I'll put it right back. Suppose you're having an argument with somebody. And you're facing each other, screaming at each other, and you each turn and walk away. You can't continue the argument because everything is spreading apart. Okay, it doesn't make sense. So this allowed scientists to come out with all kinds of weird ideas of dark matter and dark energy and string theory and stuff like that I don't understand. Tried to read about it, don't understand. But that's the major sticking point with the Big Bang Theory. This is a theory that scientists accept. They will agree that the evidence is very flimsy, but it's the only one that have some proof to support. Okay? Question?
Yeah, I was saying, sometimes when things explode, as they're spreading out, they can bump into each other. So is that possible?
There was nothing there to begin with. That's the problem. The things that that make the atoms were spreading away. So I don't know. I mean, it sounds logical. I wasn't there at the time. Okay? Yes, this is corny. Adam, wake up. Did you hear a Big Bang? Okay. Corny. Okay. Now, second theory we're going to take a look at is a little bit easier to understand. The Big Bang Theory is way up here. Okay? This one makes much more sense. We're going to take a look at where the solar system came from. Solar, if you just take apart that word, sol means sun. Just means sun system. Suns and stars are exactly the same things. We're going to take a look at where our solar systems came from and all the objects in it. The theory is called the dust cloud theory. The dust cloud theory is also called the nebular theory. Dust cloud is easier to use. What it says is that there was a huge cloud of dust and gas in space, and that's what we're taking a look at here. And contrary to what you think, gravity does exist in outer space. Okay? It's a very weak force, but it is there. And gravity started to pull together that dust and gas. So it started to contract. These are huge, gigantic clouds. Right? 90% of all of the stuff in that cloud ends up in the very center, which would make sense because everything's being pulled like this. 90% ends up in the very center and gets squished tighter and tighter. The remaining 10% remains on the outside and clumps together in littler, smaller pieces. Eventually what happens is that we end up seeing objects clumping on the outside but continuing to stay there, right? They're not falling into the center, okay? Then, as they clump together, this once cloudy stuff looks a little bit more clear. And because so much material gets squeezed in toward the very center, temperature had to start going up. And as the temperature went up, eventually what happens is that hydrogen atoms, which have the same charge, picture two magnets, north poles, God bless you. If I bring the north poles together, they push each other away. Well, the force here of the gravitational compression was so strong that it forces these same charged particles together, makes them join together, like the letters joining together to make the words. We get something called helium.
So you're saying the heat pushed them together?
No, the heat resulted from that. It's the gravitational compression that pulled them together. Oh, okay. Maybe I didn't say that clearly, like I should have. Right. Eventually, the inside of that big lump in the middle hit about 27 million degrees Fahrenheit. I'm giving you Fahrenheit because that's going to make much more sense than centigrade or kelvins. And when that happened, we have a sun or a star forming. It has to get really, really, really hot. There has to be a huge amount of material being pulled together by gravity to force the hydrogen atoms together in order to make suns. Okay? All of the stuff on the outside did not get pulled into that star or sun, but eventually formed the other objects that we have in space. The idea was that this occurred approximately 4.6 billion years ago. BY stands for billion. Okay? The entire universe itself, roughly 13.82 billion years ago. So this is much closer to the present time. So the rest that forms will be the planets, and we have comets. This is a nice picture of a comet. You can see there are actually two tails here. The glowing part is what we usually see. As soon as the comet gets near Jupiter, it will form the tail. But when it's not near Jupiter, when it's further out, it looks like this. This is comet 67P. That's it right here. Almost looks like a big dog. And then superimposed on this, you can see mountains. That's what a comet really looks like before it starts to glow. We also have rocks in outer space that we would call asteroids. This is a close-up of an asteroid. These will have formed at the same time, roughly 4.6 billion years ago. And of course, we have our moon plus the other moons. So all of that occurred at the same time. What that means is that everything in our solar system is made out of the same stuff, right? The same chemicals. So this shows you a progression from the dust cloud, getting closer and closer together, everything clumping, eventually a star turning on, and then objects surrounding it. This is not made by somebody who is sitting in a chair thinking, oh, it must be this way. When we take a look, I don't know if you can see this very clearly. Right here, you should see the three stars that make up the belt of Orion, right there. And if you look in this area here, right there where the sword is, what we find when we use a very powerful telescope is that in that sword, it's really cloudy. And we can see some glowing objects with what looks like a disc or some fuzzy stuff surrounding them. Each of those are stars that are forming solar systems. So they see different pictures of solar systems in different stages of formation and just put them together. Okay? Now, there was a theory called the cold accretion theory of planet formation. They call it cold accretion because they're talking about temperature, and accretion means clumping together. Okay? What this is actually part of the dust cloud theory, I guess we could say. What it says is that once those clumpy things formed the planets, they were cold. They had to form cold. We're going to see later. We're going to see later why that is so important. Okay? Eventually, what happened was that the temperature of those objects that we now call planets had to increase. And it increased, the temperature increased because of a couple of things. If you take a hammer and smash a nail a couple of times and then touch the nail, it's really hot. When you drive your car, if you have a flat tire and you get out and you immediately touch the tire because you're going to change it, you have to be careful because you're going to burn your hands. When the meteorites way back in time, smashed into the earth, they actually left their energy behind in the form of heat. So that made these objects heat up. Second thing is called gravitational compression. And gravitational compression is what they used to do in, I guess, the 1940s or 50s or something like that. I know some of you are not going to recognize this thing. This is called a telephone booth because people used to have to go to these pay telephones. They would go in a booth and shut the door and use the phone, right? For some weird reason, the teenagers like to squeeze themselves into that because I guess that was fun, right? It would get very hot in there because you're squeezing too many people in there. Well, the same thing happened with the planets. As gravity continued to pull everything closer and closer, the temperature had to heat up. That's called gravitational compression. We also had radioactive decay, right? Radioactive decay is something that is actually pretty nasty. The picture shows you a radioactive pellet right here. One of the byproducts of radioactive decay is heat, okay? In the picture over here, you can see somebody has a pretty nasty sunburn. That's a radiation burn. Tremendous amount of heat can be released. The idea was that the radioactive materials on the inside of these planets was also producing some heat. Now, once that heat is produced, heated up the inside, that then allowed the inside to start to separate into different layers. Before you put salad dressing on your salad, what do you have to do to it?
Shake it, mix it.
Got to shake it because everything in there separates. The inside of the earth was really hot, and it started to separate into different layers. Heavier stuff fell down to the inside, which would make sense. Throw a rock in the water, it sinks. And then gases pop out. Right, this is not a gas. The gas is back here. The gases had to be released because they are less dense. Right? And that brings us to our planet. Okay, that object in space that has everything that we need on it. This is something that we study. One of the ways that we study it is by using what we call a globe. Okay? That's what we're going to be taking a look at. We're going to do, as I said, we're going to do your first lab. This is a very simple one. You can write on this piece of paper. I am not going to collect this from you. Okay? We're going to be using some globes, and we're going to be taking a look at a number of different regions of the globe. Now, we are supposed to have 8 different globes. But unfortunately, my colleagues have a habit of taking them to other places and never returning them. So what that means is that you're going to have to share them. So if you tend to be a little bit antisocial, I apologize. You're going to have to clump up with people. Maybe you three can work together. Maybe you three can work together. One of 6. Maybe you three can work together.
What's your nationality?
Cuba.
Cuba?
You? Where are you from?
Guate, Honduras,
Where are you from? What those country?
3 countries.
Yes.
But you're not ciudadano.
Do you speak Spanish, no?
Poquito. Pero entiendo todo.
Yes. I've been living only less than 2 years here in the United States, so I have some problem with my English. I try to.
But if you stay here, like, you learn it fast.
Yes,
You know what
yes,
I mean?
yes. I'm take a record of the class because I need to listen again to improve my English to understand
When you
everything.
drive, you should listen to that. If you
Yeah,
have,
yes.
Right, and with this globe lab,
When I go to there, I'll listen with my
the
friend.
nice, happy, smiling person. We're going to be looking at a bunch of different regions on the globe. In the first part, we're going to look at the Arctic region. And the problem that you're going to find is that at the very top, where the Arctic region is, there is a disk. and that blocks what you're supposed to see. All right, in some cases I think it's a green disc. Right? It would be really nice if they didn't have it there. Like, you might have to try to look underneath it. It would be nice if we could just remove the disc, and that way you would be able to see how much water there is actually there. Okay. In the second part, we're going to look at the Antarctic region. And in this case here, I don't know if you can tell from this picture, but the Earth has been flipped upside down. You can do that if you choose. What should be very surprising is how large Antarctica actually is. It is a massive continent. If we put it on top of the United States, it would cover the whole planet. Okay, it's a gigantic place. In the third part, we're going to be looking at the ocean region. And what I'm showing you here is something that's called the Mid-Atlantic Ridge, part of the mid-ocean ridge system. It looks like a gigantic zipper. You're going to be looking at that. The Hawaiian, sorry, this is a really dark picture. The Hawaiian Islands are going to be located in number 7. When you look at the Hawaiian Islands, because the globe is bumpy, you'll be able to trace the Hawaiian Islands going a fairly long distance, even though they're going to be underwater. In the next section, we're going to look at the land and ocean mountains. This is a picture of High Point, New Jersey. High Point is the highest point in New Jersey. It goes up 1,803 feet above sea level. There's a war memorial on top there. You can actually climb all the way to the top now. Look out the windows. You can actually see 3 states. When you look for these different mountains to find out which is the highest above sea level, it will say next to the name of the mountain what its elevation is. Then from 9, owning the islands. When you take a look at Ireland here, Northern Ireland is still part of Ireland, but the UK owns it, so you'll look in parentheses, and that will tell you who owns those islands. In the last section, we're going to take a look at some other things. The equator is this line over here. It cuts the globe in half in this untilted Earth. On those globes, it's pretty easy to find the equator because they have it really nicely darkened down. The international dateline, on the other hand, is a little hard for you to find. In between Siberia on the left and Alaska on the right, there are these little islands that are called Big and Little Diomede Islands. The international dateline will be able to be seen right there. This is what they look like. They're fairly close together. They are so close that people sometimes walk across or take boats, but that's illegal because it's a different country.
Oh, yeah.
You can see the international dateline bends. I think it's red on the globes. Okay? So why don't you try to find those? If you can't find, well, we can look at the stars. They appear to make trails going around. That's what you can see in this picture. Barely see in this picture. It's not light enough, but that's where the pole star is, Polaris, and these are the star trails. This is a time-lapse photograph. So it's showing you the path of the star as it's going, as it appears to be going around us, even though we're turning. The focal pendulum is what you see over here. If you go to the National Smithsonian, they used to have one of those. I don't know if they still have it. It's a big heavy ball that just moves back and forth like this. And as the Earth turns underneath it, the ball knocks down spikes. It's on a almost a frictionless thing at the top that allows it to do that. The Coriolis effect is something that you might be familiar with. This is something that was discovered, I guess it was embarrassing to the Germans during World War I or II, I don't remember which one, but they would aim directly at Paris with their missiles and miss. And the Germans were very known to be very precise. And they said, we're aiming right at it, how come we're missing? Because the Earth is turning underneath it. They didn't compensate for that. If you're going to throw a ball at somebody and they're running this way, you have to throw it ahead of them. They didn't know that. These all supported the idea that the Earth turns on its axis. So these are ideas that people came out with way before they had computers and space travel and stuff like that. If you take a look at Polaris, from our latitude, you're going to see that it is almost halfway up in the sky. But if you go to the North Pole, you're going to see it almost directly over our head. Right? Our North Pole points almost directly at Polaris. Number 2, our planet here, plus the other planets and the moons and everything else, revolves, which is a lunar base, around our sun. That means they turn around our sun. The entire disk, or cloudy stuff that form the sun, spins around like this. Occasionally there are things that whiz in from different places in outer space and go the other direction, such as some comets. But whatever balloons in our solar system tends to move in the same direction. That would support the idea that the entire solar system formed at the same time, out of the same cloud. Okay? And I'm giving you the speed there. They estimate that this whole thing is turning 66,000 miles an hour. It's pretty fast. Can I switch? Movie needs? We have a number of proofs that show us that we do go around the sun. There is something called parallax, which sounds very complicated. What it means is this. Let's suppose you are on the Earth looking at a nearby star. Here you are, you see that star. You'll see those stars in the background. 6 months later, when you're on that side of the Earth looking at the same exact star, you're going to see these stars in the background, completely different stars. Our angle of view has changed. And that's called parallax. As we go around our sun, we're going to notice that. Changing length of days, that's something that you hopefully have been noticing over the past month or so. Sun's going down a little bit earlier every day, roughly a minute every day. And by the time we get to December, we're going to have only 9 hours of sunshine rather than 15. Okay? Changing constellation patterns. If you go outside and you look at the constellations, which are getting more and more difficult to see these days, but you will see that there are different constellations every single season. You're familiar with the zodiac constellations. Okay? Those are the ones that are probably most obvious to see changing. Bless you. Number 3 has to do with the size of the Earth. There was a very famous Greek thinker called Aristarchus of Samos. Here is a pillar, or a spike, or I forget exactly what, this was a well, I'm sorry. That was a pillar. This was near the equator, this was in Egypt. And he noticed that at a certain time of the year, on the equator, a certain day, there was no shadow when the sun was overhead directly at noon, no shadow in this well. But over here, there was a shadow. So what he had a person do was to walk from here to here, face out the distance. And he figured out what this angle was. He looked at the angle of the shadow, and from that complicated math, he was able to calculate the distance going all the way around the sun. Sorry, all the way around the Earth. This is in the 3rd century BC. That's pretty impressive. The only thing is we didn't know what units he used, but he actually calculated the distance going all the way around the Earth, just based on very simple trigonometry. If we go completely around the equator, the distance is 24,902 miles. If we go from the North Pole down to the South Pole and back up to the North Pole, we don't get the same number. We get 24,860 miles. So there was a 42-mile difference. That's roughly the distance from where we are to where Trenton would be located, this part of New Jersey. 42 miles difference. The reason why there is a difference is something that I said before. I'm going to use this globe again. As the Earth is spinning on its axis like this, everything that's at the north and south region moves toward the equator. It bulges in the middle. So in other words, our Earth is not perfectly spherical. If you take a telescope and look at the planet Saturn, it will look very oval-shaped. Forget about the rings, just the planet. And that's because it's a gas giant planet. So it's more bulging in the middle. Our Earth is rocky. So it's taken quite some time to have that difference of 42 miles. Can I move it? Okay, number 4 has to do with the shape. The official name for the shape of our Earth is an oblate spheroid. Okay, the term oblate spheroid means flat on top, flat on bottom, like a sphere. Normal people call it oval. Oval is fine. Okay? Or in other words, from North Pole to South Pole to North Pole and around the equator is not the same. So our Earth is slightly oval shaped. Okay? And this is because it spins on its axis. This is something that Sir Isaac Newton figured out a long time ago. Okay? There are tons and tons of proofs that we have of the shape. When you take a look at a ship, such as this sailing over the horizon, the whole thing doesn't drop off. The bottom disappears first, and then later on the sails disappear. If you watch somebody go down an escalator, you're going to see the same thing. Their feet disappear first, then eventually the rest of them. Okay? If you take a look at the shadow of the Earth on the Moon, it's curved. When you look at different stars in the sky, go to different latitudes, you see different patterns. Sunlight angle will change at different latitudes. If you have ever been down to Florida and you go outside at noon, it's very hot, you have a very, very short shadow. You go way up to the polar regions, you have a much longer shadow. Space photographs are pretty obvious, definite proof. And there are differences between latitudes, but we'll come back to that later. So we have tons of proof that shows that the Earth has that shape. Now, almost everything that I showed you here was figured out by people way before they had all of the technology that we have today, which is actually fairly impressive. That's what a lot of the measurements were based on, and from that they developed almost everything that we have today. Yeah.
How far do you think a ship has to go into the sea until you see it going down because of the curvature?
That's a good question. I don't know the answer to that. That's a good question. I bet I could probably work that out mathematically if I could figure out find some formulas, but honestly, I don't know. I've never stood down the shore and watched the ship sailing away. Okay, I've only seen them sail past.
Depending on how tall is the ship.
That is the end of that unit, the introductory unit.
Huh?
On
That depends how tall is the ship.
Thursday. Because usually I teach this class Monday and Wednesday, so probably gonna screw up on days. On those days, what we're gonna be doing, since we've taken a look at the globe, we're gonna go into mapping.